Hi guys, in this presentation we shall learn about floating point representation. Okay, so most people know that actually how to convert these numbers into the form that is stored in the computer. Okay, but the logic behind it is not known. So in this video I will try to explain the logic behind it. Okay, so before understanding this floating point representation we should know the basic fundamentals. We'll see here. You can see that what is the common in all these numbers. You can see here the dot is a fixed position is there for all these numbers, so this is called a fixed point numbers. Okay, now you can see here the dot is at this position, here the dot is at this position, here the dot is at this position, which means the dot is floating. Okay, so that's why these are called floating point numbers. So why we need to store these numbers? First of all, we can think like whenever we do some calculations, we always represent a number in floating point, right? Some scientific calculations, we get a number, will get a number in real numbers, right? Not like integers. How to store these numbers? So the logic is convert these floating numbers into fixed numbers, fixed point representation, and store the numbers in the computer. But how to convert this? In order to convert this floating point number into a fixed point number, that is called, technically it's called normalization. So what does it mean? This can be written as 8.49 into 10 to the power of minus 1. This can be written as 9.99 into 10 to the power of 2. This can be written as 8.45 into 10 to the power of 0. So in this fixed position, I have fixed like there should be only one non-digit number before the dot, which means see here the dot, before this only one non-digit number. Okay, so that is how I fixed this. So you can see that here the point is here there is no point, here the point is there. So I have converted all into a fixed point representation. So in order to understand the binary concept, I have explained you in the decimal system. Now we will go into binary system. Suppose I have taken a number and I convert into binary, then this is how it represents. Okay, so how can I normalize this? Same logic, 1.10100 into, since here the base is 2, I have to use here 2. Okay, 2 power 2. Now here you can see that 1.111001 into 2 power 3. Since here minus is there, I'll put minus here. Okay, here we can write like 1.010 into 2 power minus 4. Okay, so how we can store these numbers in computers? So in this there are 4 bytes are allocated. 4 bytes, in this 4 bytes are allocated, which means there are 32 bits are allocated. So at the top you can see that here there are some numbers. Okay, I'll take this number for example. Okay, 1.010 into 2 power minus 4. So there are 32 bits are there, so they are divided into 3 sections. This is, we store sign of the number, and here we store exponent, and here we store mantissa. Okay, mantissa, it takes 23 bits, exponent 8 bits, and sign bit 1 bit. Here what is the part after this dot? Okay, 010, that is stored in mantissa, like 010. If there are no numbers, then there will be all zeros up to these 23 bits. Okay, now here this minus 4 is stored in this exponent form, but not directly. Okay, we'll add 127 to the exponent, whatever the exponent may be, and we'll store that binary equivalent in this exponent. Okay, since here it's a positive value, we'll store 0 here. If it is a negative value, we store a 1 here. Okay, so this is how we store the number. my first question is, why use in this form? Okay, why 23 bits are allocated, why here 8 bits are allocated, okay, why this should be done, okay, why, everything I want to know. Consider you as an engineer, okay. So as an engineer, if I given a task like store a floating point number in a computer, so usually the first idea is like storing the integer part separately and fractional part separately, for example like this, okay. For storing this, what we'll do, we'll take a memory location in which we divide three sections. One section is for a fractional part, one section is for integer part, and another section is for sign part. Since sign is of only 1 bit, here 1 bit, okay. Here it's a fraction part, here this integer part 23 and 45, okay. So this is how we store. Now my first question is, how many bits are allocated for fractional part and for integer part? So this is the first idea behind this floating point representation. So usually in scientific calculations, we usually use 7 to 8 significant digits, okay, significant digit precision we use. So in order to store one decimal number in binary, we need 3.2 bits, which means you can see like this calculation, 10 log 2 to the log 10 to the base 2, we will get 3.2 bits, okay. So my idea is like, in order to store 7 to 8 decimal numbers, we need approximately 26 bits. So usually in computer we use data in terms of bytes, right? So the least amount of bytes will required is 4, because if you take 3 it will be 24 bits, okay. If you take 4 we will get 32 bits, okay. So in that 23 bits are allocated to fractional part and remaining bits are allocated to sign and integer part, okay. The maximum value we can store by using this method will be 1 1 1 1 1 all ones up to 23 bits, and dot here all ones in fraction part also up to 8 bits, okay. So you'll get an answer like 16 77 21 5 dot 998, okay. So this is the maximum value we can store using this logic, okay. So what is the smallest value you can store, what is the minimum value? Again the same logic, all 23 bits are 0, okay, all 23 bits are 0, and in here the last position is 1 and all remaining are 0. So the least value we can store is 0.00390625, okay. These are the key points in this technique, right? So as an engineer, you design a technique in which we can store this is the maximum value and this is the minimum value, okay. So now why we need to go to that approach, okay. See, now we need to increase this capacity, okay. So how can we do that? So they have some idea that is not like this, okay. What they said that, okay, they'll take sine, exponent and mantissa. So how they're gonna store using that technique, we'll see. Whatever the number is given, for example, I'll consider like 0 0 1 1 0 dot 100, okay. So first we need to normalize it, so it will look like 1.10100 into 2 to the power of 2, okay. So in order to store this, we have some a fixed format, right? That is sine, exponent and mantissa. Already we discussed that in order to store a significant digit precision we need 23 bits, okay. So that's why this is allocated here, and here we add 127 to the exponent. So why? The question is, why we add 127? In order to answer that, first we need to understand the 8-bit logic here. Since there are 8 bits, you will get like 0 to 255. The total is 256, right? So in this total, what we are doing is 127 plus exponent. You can think like, if I add is 127 is half of it, then there are two values remaining it. Like you can see that if I reduce 2, I'll get 254. Okay, 127 into 2, or 127 plus 127 is 254. Okay, there is a number 127. Okay, and in order to get 124, I can add up to 127. This is the maximum value here, and here I can add negative numbers also. So I'll get here up to 1. Okay, so my point is, so there is a number after that 0 and here 255. For the time being, consider these numbers are not considered in this exponent form. Okay, only if I want to store the positive value, then I'll use this range. If I want to store the negative value, I'll use this range. Okay, so this is used to store the positive and negative values in a fixed memory. Like in usually in computers we store 2's complement form. Now in this case we use this biasing method. Okay, here I can store positive numbers and here I can store negative numbers. Okay, so you may think like, what is this sign bit here? Don't confuse sign with exponent. Here see here, for example, this is a number in which here there is a minus and here there is a plus, then this minus is stored here. Okay, so this sign indicates the number is positive or negative. Okay, whereas this exponent indicates whether to move this dot to right or left. It depends on whether it's positive or negative, whatever it may be. Okay, so understand the difference between them. Okay, you can see here we got here a negative number as well as positive number. Okay, so for this purpose we add bias to it. Okay, we bias the exponent. Okay, so we got our two reasons. One is why you use 23 bits, and second one is why we use biasing. Okay, why we add 127 to it. Okay, in order to store this number. So what is the largest number we can store using this technique? We can see that if I store the largest number, like here sign bit is 0, all the values should be 1, but there is a condition, right? Here all the values are 1 except the last one. I'll tell the reason why. And here all the values are 1. Okay, 23 bits all 1. Here 23 bits are 1, here 8 bits in which all are 1 except this bit. And if you calculate this value, we will get 3.403 into 10 to the power of 38. So my first question is, why we left these numbers? Now this is a very interesting case. See, so what is the smallest number we can store using this format? You can see here the 0 0 0 all up to 1, here all zeros. Okay, so the answer will be 1.1755 into 10 to the power of minus 38. Okay, so this is the largest number and this is the smallest number. Now you can compare these results with the previous results. Okay, so how big difference is there? So in order to store that much of huge capacity of numbers or that much of precision, we need to use this method. Okay, now the question is how we store the zeros and infinities in these numbers. Whenever there is a 0, sign bit is either 0 or 1. Okay, sign bit is either 0 or 1, we don't care. Exponent, this is the main point, is all should be 0. Okay, in both cases, if exponents all should be 0 and mantissa also zeros, then the number is represented as 0. Okay, so how infinite is represented? Infinite is represented again 0 or 1, we don't care. Exponent all ones. Okay, exponent all ones, all 8-bit ones. Okay, 8 bits ones. Okay, mantissa all zeros. So this is for representing infinity. So you can see some pattern here. If exponents all are 0, then you can get the value 0. If exponent all are 1, then you will get the value 255. So that is the reason why here 0 and 255 are not included in this condition, due to this reason. So 0 is allocated to represent value 0 and 255 is allocated to represent infinity. There are some operations like 0 by 0, infinity by infinity, etc. So this doesn't have a number. Okay, this it's called a not a number, nan. Okay, and it's called QNAN, and some are signaling NANs, which means this is the maximum value and this is the minimum value. So what happens if after calculation, if I get a number which is larger than this or smaller than this, then it is represented like SNAN, okay, signaling NAN. So in order to represent that also, there is some uh, rule, like exponents all should be ones, and the mantissa should be leading with number 1. Okay, so this is the criteria to represent it as a QNAN. For SNAN, again the exponent should all ones, but the leading should be 0 and remaining at any part it should be a 1. So this represents SAN. Okay, so this is the logic behind the floating point representation. So we'll just solve an example, so we'll get a picture, a clear idea about it. Okay, 0 1 0 1 dot 0 0 0 1. Okay, now first idea is to normalize the number. To normalize the number, we have to shift this dot to this position. Okay, after shifting we'll get like 0 1 dot 0 1 0 0 0 1 into, since it's a base 2 system, 2 to the power 2. Okay, since it is shifted left, it is positive value. If it's shifted right, we will get a negative value. Okay, now after this we know that in floating point representation we have three parts: sign, mantissa and exponent, right? Since it's a positive value, we'll store here 0. Okay, it should be biased, right? So 127 plus 2 is 129. So in this exponent there will be 129 binaries equivalent. Okay, convert the 129 binary, that value will be in exponent, and then in mantissa the remaining part will be there. The remaining part is 0 1 0 0 0 1 and remaining numbers are 0. So this is how we represent. So how to get the number back to form? So use your common sense. First we will use sign convention. In order to get plus, I can simply write like minus 1 to the power of 0. If s is 1, we will get minus 1. If s is 0, we will get 1, positive 1. So I can, in place of 0, I will replace with s. Okay, and after that, since we are storing this part in mantissa, this is we are neglecting because we already knew that we are normalizing. So in this we have to represent like 1 dot this mantissa like 0 1 0 0 1 into, since we are adding 127, here we have to subtract it, right, to this number 129 minus 127. So after calculating we will get minus 1. Okay, so not minus 1, s is 0, right? So plus 1 1 1 dot 0 1 0 0 1 into, after subtraction we will get 2 power 2. Okay, if you do operation, if you remove this, we will get like again the original number. Okay, so in generic form you can write like minus 1 to the power of s. Okay, 1 point mantissa into 2 power whatever the exponent minus 127. So this is how we retrieve the data from this. Okay, I hope you clear the doubts about this floating point representation. So the same logic is applied for 64-bit representation also, in which the size will increase. Okay, here the mantissa will be 52 bits, in exponent it will be 11 bits, and here sign will be 1 bit. Okay, and since biasing also increases, okay, 10 23. Okay, same logic. If you apply the same logic, it will store a more capacity of the floating point numbers. Okay, so whenever you given a problem to solve that, first normalize the number and then bias the number. Okay, it depends on what the how many bits are there, either 32 or 64. Depending on that we have to do biasing and store the number in this format. Okay, and how to retrieve the number, same logic. Okay. For retrieving the number into 1 point into 1 point the mantissa to the power of in 1 point mantissa into 2 power exponent minus the bias. Okay, again this bias depends on the number of bits you take. Okay, for representing 0 exponent values are all 0, for representing infinity exponent all values are infinity, all 1. Okay, all ones. And for SNA, SNAN and QNAN, SNAN again exponents all are ones, all ones, and leading number should be 0, and remaining in remaining bits there should be at least 1 in that. And QNAN in exponent all the values should be 1, and